Today's notes are for part 2 of Standard 17. You'll need in-class 73 to follow along. We're going to start with some key ideas, and then we'll have some examples and some conclusions to make as a result of our work. All right, so when we're looking at angles with vertices on circles, there are a couple of different ways that can look. We've got an example here where point A is on the circle, and the angle itself then heads off with two rays to intersect the circle at B and C. So that would be an angle that has an vertex on the circle. When we look down here at this picture, the vertex would be B on the circle, and so then the angle would head out towards A and keep going, and then C and keep going. And then when we look at the last picture, it looks a little bit different, but our vertex on the circle is right here at B. So we actually have two different angles. We could head towards D and out this direction, which would be trapping angle 1 right here. Or we could go backwards. We're still heading out towards D, but then out this direction, and then angle 2 would be the angle that has a vertex on the circle. So a couple different ways that can look, but in general, what we're going to be looking for is what we call an intercepted arc. That's going to be an arc that lies in the interior of an inscribed angle. We'll talk in a second about what an inscribed angle is. It's going to have endpoints that are on the circle. And in this picture right here, the intercepted arc is in between B and C. So we would call it arc BC or arc CB. Either one would work. So if you imagine starting at the vertex, I usually put my fingertips at the vertex, follow out along the sides of that angle, and then the intercepted arc is the one that gets trapped in between your fingers when you're at the point where you intersect the circle. All right, inscribed angle was used in that definition. So let's talk about what an inscribed angle is next. That's going to be an angle whose vertex is on a circle and whose sides contain points of the circle. And so what that means is that if we have a vertex on the circle, we travel out basically with a chord, we're going to have another point on the circle. Same thing on the other side, another point on the circle. So that inscribed angle is created from basically two chords that extend past that circle boundary then, and then the angle in between them. According to the inscribed angle theorem, we can solve for either the intercepted arc or the angle itself. We actually got you ready for this inscribed angle theorem at the end of yesterday's notes. So I'm going to pull that back real quick here. This is the end of in-class 73. We did these two examples here at the end where we actually previewed what's going to be true for inscribed angles. If you look, we have an inscribed angle right here. The vertex D is on the circle. This side is a chord, this side is another chord, and we solved for that by using this little isosceles triangle. However, we could also look at the relationship a different way. This intercepted arc right here is going to match this central angle measure, so 102 degrees. We figured out this inscribed angle, which was angle ADE, was 51. There is most definitely a relationship between 51 degrees and 102 degrees. Do you know what it is? We're going to come back here and we're going to fill it in. Inscribed angles are going to have a measure that is equal to half the measure of the intercepted arc. In that example that I just showed you from yesterday, the arc was 102. Half of 102 is 51, and that's exactly how big that angle turned out to be. So if we're looking at this picture here, angle B is an inscribed angle that intercepts this arc right here between A and C. So the measure of angle B is going to be the measure of arc AC divided in half. So you can divide by 2, you can multiply by a half. There's lots of different ways you can do that. Or you can move the 2 to the other side of the equation, and you can say that twice the measure of angle B, so 2 of the angles, equals the measure of the arc. The key is that the arc is always bigger. So from that example before, maybe we'll just steal those numbers. If this is 102 degrees, the angle will be 51 degrees. Okay. The same thing is going to be true for this other type of angle with a vertex on the circle. These angles are called tangent chord angles. And so this is going to occur when a tangent and a chord, not very creative, intersect at a point. So we have our tangent out here, and then we have our chord right here, chord BD. They're intersecting at a point B. It's very important that that point where they intersect is on the circle. And when that happens, the measure of each angle formed, so both angle 1 and angle 2, are going to have the same relationship as inscribed angles. They'll be half of the measure of the intercepted arc. So if we're looking at the measure of angle 1, we're going to travel out. The intercepted arc for angle 1 is a major arc. It's this very large, more than halfway around arc. So we're going to call that the measure of arc BRD. Remember, 3 letters. When it's a major arc, divided by 2. If we look at angle 2, we're going to go the other direction. So we're heading out from B the other way, and our intercepted arc is right in here. Ooh, sorry about that. So that's going to be a minor arc, which means we only need the endpoints B and D. So the measure of arc BD still divided by 2. Half the measure of the intercepted arc anytime the vertex is on the circle. All right, let's go ahead and look at some examples. Let's see what else we've got going on here. Our goal for number 1 is to find the measure of angle DBC. So I'm going to highlight that. This picture doesn't have a lot going on, but some pictures do, so it kind of helps to kind of see what's going on here. That angle has a vertex on the circle at B. So if we follow it out, our intercepted arc is over here, 134. The angle is half the arc. So the measure of angle DBC is going to be half of 134. And that'll be 67 degrees when you do that calculation. If we're moving over here to example number 2, they're asking us to find the measure of angle RQT. So RQT is the goal. That's going to be this angle right here. Well, I'm noticing an issue. If I follow that out, then the arc that I need is right here, this major arc. But I don't see a measurement as I travel that arc. I see a measurement on the opposite side of the picture. So there are 2 approaches that you can take when this happens. Approach number 1, you fill this arc in over here. The rest of the circle is 112. So if we take 360 and subtract 112, that will tell us that this arc turns out to be 248 degrees. There's only 2 arcs that this circle was split up into, so that subtraction will help move us to the other arc in the diagram. Now that we're to the correct intercepted arc, the measure of angle RQT is going to be half the measure of the intercepted arc. Half of 248 is 124 degrees. So that's one option. The other option, let me see if I can switch to a different color just so I can show that, is to actually find this angle over here. It's still an angle with a vertex on the circle, but the intercepted arc this time is available. It's 112. So if I'm looking for this angle, 112 divided by 2 will tell me what that angle is equal to. That's going to turn out to be a 56-degree angle. This is a tangent line, and we know straight lines add up to be 180. So if I know this part of that linear pair, all the way back from standard 2, We're going to subtract 56 from 180, and sure enough, we end up with 124 degrees for that angle, just like we found out earlier, but for a completely different set of reasons. With these problems, there's often more than one way to solve. It's not going to matter to us how you solve, you just need to make sure you're solving carefully. All right, number 3, they've asked us to find the measure of angle HFG. So if we look at angle HFG, this corner up here is the one they want us to focus in on. That vertex is on the circle, so I'm going to travel out, and my intercepted arc is over here. I'm hopeful that you noticed something special about this segment right there. That goes through the center of the circle. So even though it's not measured, or not marked, this is a semicircle, which means it's 180 degrees. So our inscribed angle, our angle on the circle, is going to end up being 90 degrees. That comes from doing our 180 degree semicircle divided by 2. That's actually something that you can watch for. When you have an inscribed angle, that intercepts a semicircle, or that is connected to a diameter, is another way of thinking about it. It will always end up being a right angle. Okay, let's see what we have here in number 4. Number 4 looks a little bit different. They're not really starting us off with arcs like we had in the previous examples. They're starting us out with an angle. The ultimate goal of this problem is for us to be able to figure out the measure of angle KJN. I'm going to continue that angle out because I noticed the vertex was on the circle, so I really need to be able to follow the angle all the way to the circle to be able to know what arc matters. That's my intercepted arc between K and L. So in order to find this angle, I would need to know how big this arc is, and then I would divide it by 2. Well, that arc is empty, so I need to go searching for other information. The only other information I see, since there's nothing going through the center, we don't have semicircles to use this time, I see this 42 degree angle up here. So let's follow that out from the vertex that's on the circle as well, and look at what happened. That orange intercepted angle that started at point M on the circle intercepts the same exact arc as this angle J that I'm looking for. That means that they're going to be exactly the same size, but let's make sure we understand why. If this angle is 42, that means that this arc must be 2 times 42. That's using this relationship right here from our inscribed angle theorem. 2 times the angle measure equals the arc measure. So that means I could fill this in as being 84 degrees, and then I would just work it backwards. To find this angle on the circle, I take my arc measure and I divide it by 2, which sure enough turns out to be exactly congruent to that other inscribed angle. So if we have 2 inscribed angles, 2 angles that have vertices on the circle that intercept the same arc, they are going to be congruent. There's no other way around it. All right, let's go ahead and flip the page and I'll meet you back here for a few more examples. A lot of times these problems can start to look kind of overwhelming. You really have to take your time and think about what all of these clues can be useful for. So try to make sure that you're not just rushing yourself through trying to get through fast because they're only asking you to find one thing. Sometimes that takes some serious effort. All right, our goal for this problem, it looks like, is to figure out what the measure of arc CD is equal to. So I'm going to highlight that orange just so that my brain can focus on it. That arc is the goal. I don't see a way to use the other arcs to get there. because I don't have enough to use 360. I don't see anything going straight through my center to be a diameter or a semicircle. So I think I must need to use some of these other angles that are on the inside of the circle. Now I know how to use angles that are at the center, which we don't have any, and I know how to use angles that are on the circle. We have not yet learned how to use angles that are inside the circle in some random location. So I'm going to avoid this 102 unless I absolutely must use it. And I'm going to focus on this 55-degree angle instead because it looks a whole lot like what we just learned about on the last page. Vertex is on the circle, so we're going to follow that out. And sure enough, this arc I'm looking for is the intercepted arc. Remember, the angle is smaller than the arc. So I need to do 2 times the angle measure to find my arc measure. And that's going to turn out to be 110 degrees for this example. So all those other numbers, the 102 degrees, the 87 degrees, those were all just distractors, things that we didn't end up really needing to use. And that happens sometimes. So you want to understand that you're not going to use every single detail of what they put in the picture sometimes. All right, moving on to example B. Our goal is to track down x. We have 2 x's in the picture. So those both look like they have vertices on the circle. So if I knew what this arc was equal to, I might be able to write an equation to solve for that x using 4x minus 11. But this is empty. So I'm going to move on to the other piece of information that involves x. And I notice it's the same kind of angle. It has a vertex on the circle as well. And so even though this arc is a mystery, since these are both inscribed angles and they both intercept this same arc, I know that they're going to be congruent based on that conclusion we just made at the bottom of the last page. Congruent is the same as equal when we're shifting into algebra mode. So we're going to set these equal to each other. And then solve just using our algebra skills like we've done so many other times. Subtract 2x from both sides, add 11 to both sides. Looks like x is going to turn out to be 16. Now there could be times when they ask you not necessarily just to solve for x, but they ask you to find this arc. That means we would need to plug our x in, and then because that's an angle, we would double it, multiply it by 2. And then we would be up to where that arc measure is given to us. All right, continuing on here. We've got a question here with C that doesn't have any values in it at all. Sorry about that. Somebody came into the room to collect the garbage. All right, so when we're looking at this, I am noticing that we do have something going straight through the middle of this circle. So that's going to be a diameter, which means we're probably going to end up with some 90-degree angles here because it looks like that vertex is on the circle, and sure enough, it intersects that semicircle, which means it's going to be half of 180 degrees. Angle 2 is going to be the same thing. They just shifted over a little bit, but the vertex is still on the circle and it still intercepts that same semicircle that's 180 degrees. So both angles are going to be 90 degrees in that example. Onward to letter D here. I'm noticing a couple of details here. I've got a 35-degree angle that does look like the kind I've learned about today. So if I follow out from that vertex, it's going to give me information about this intercepted arc over here. If the angle is 35, I need to make sure I do 2 times 35 to figure out what this arc measure is. Now you might be asking, why are you doing that? It's not asking you for any arcs. I know, but it is asking me for a lot of other angles. So if I have that filled in, it might help me with some of the other angles. I'm also noticing this right angle box here. Now look at that vertex. That's not at the center and it's not on the circle. So we don't know how to use this angle to tell us about arcs yet. In fact, we can see that this angle is 90 and that arc that it intercepts is 70. So they're definitely not equal and they're definitely not half or double. But what that 90-degree angle could help me with is to recognize that we've got linear pairs here. This is a nice straight line. So if this angle is 90, I can do 180 minus 90 and figure out that this one is also 90. Or I could use vertical angles and I could fill out this one as being 90. Or this one as being 90. In fact, all four of those end up being 90. And so I'm kind of noticing, maybe without even new circle stuff, that we have the opportunity to use our triangle sum theorem here. All three angles in a triangle add up to be 180. So if we subtract 35 and we subtract 90, angle 1 is going to turn out to be 55 degrees. If we're looking down here at angle 2, I'm noticing that has a vertex on the circle. So I'm going to follow it out, and sure enough, that intercepts my same 70-degree arc. So you could recalculate. You could do a 70 divided by 2 real quick to figure out what angle 2 is, or you could remember that inscribed angles attached to the same arc are congruent. So you could steal that 35 from the pink angle, and angle 2 will match it. And then if that's 35, I think we're going to end up with the same situation here for angle 3. We're in a triangle. We've got 180 minus 90 minus 35. So angle 3 is going to be 55 degrees, just like angle 1. And if you think about that, that confirms our theorem from earlier, because angle 1 intercepts this arc over here. Angle 3 intercepts that same exact arc and has a vertex on the circle just like angle 1. So we know they have to be congruent since they're the same type of angle intercepting the same arc. All right, 4 more for today. The measure of angle 1 here in part E. I see a vertex on the circle, so I'm going to follow out angle 1. There is an intercepted arc of 112 degrees trapped inside that angle. The angle is smaller than the arc, so we're going to take 112 and divide it by 2 to figure out that this angle will be 56 degrees. Okay. I'm noticing that there's an X over here, but I don't see an X in my lineup, so I'm going to go ahead and add that just because it seems like it would be a good idea to find it since it's labeled in the picture. If this arc here is 112, X looks to be the rest, that major arc over here on the other side. Remember, our arcs always add together to be 360 degrees if they cover the whole entire circle. So that means we're going to end up with 248 degrees for that major arc. And then just like earlier, we've got 2 options for how we can find angle 2. Angle 2 still has a vertex on the circle, but it intercepts this 248 degree arc. So I could take the arc and divide it by 2. That would give me 124 degrees. Or I've got a linear pair here with angle 1 and angle 2. So I could subtract my angle 1's measure from 180, and that would also confirm that that angle is 124 degrees. Onward to letter F. We've got 2 angles to find. Angle 1 here is at the center of the circle. Remember from yesterday, angles at the center are going to match their intercepted arcs. So if I knew what this measurement was, angle 1 is equal to that. Angle 2 looks like it's intercepting the same arc, but its vertex is on the circle. So it's going to be half of that arc. And hopefully visually that makes sense. This angle is bigger than that angle. Basically, when you pull that vertex back and hook it up to the edge of the circle, it ends up being half the size as if it was at the beginning, or at the center, excuse me. So I really need to know this arc to find both of these angles. And the great news is they've given me the rest of the circle. They've just given it to me in 2 pieces. So because all 3 of these arcs together make a full circle, we're going to start by subtracting the 2 that they gave us from 360. I believe that's going to turn out to be 92 degrees for that arc. Let me just double check that real fast to make sure that that subtraction is right. Yep, 92 degrees. And so since angle 1 is at the center, it matches that intercepted arc. But angle 2 is on the circle, so we're going to have to divide that 92 degrees in half to figure out what angle 2's measure is equal to. Okay, last two here. Letter G is really similar to the one right above it, letter E, except there's some algebra in the mix. Don't let that throw you off. We have this 59-degree angle right here with a vertex on the circle, and we have this arc that's intercepted by that angle, inside that angle. And so if we think about our relationship, we know that the angle is the arc divided by 2. So that would be one way to write the equation. Or we know that 2 times the angle equals the arc. So either one of these equations is acceptable. And in fact, if I start solving this one by multiplying both sides by 2 to get rid of the fraction, do you see how it turns into the second equation that I wrote anyway? So you can get away with thinking about it either way. 2 times 59 is 118. So then we're going to end up subtracting 34 and dividing by 2. You should end up with x equal to 42 by the time you finish up those calculations. All right, last one. We've got 3 things to track down here: x, measure of angle 1, and measure of angle 2. I will be honest that sometimes it's not best to try to solve for them in order, so just be aware of that. Sometimes it works, but not always. So I think I'm actually going to solve for angle 1 first, because I notice that its vertex is right here on the circle, and when I follow that out, I have an intercepted arc over here that's equal to 100. My angle will be less than my arc, so I need to take 100 and divide it by 2. And now I know the measure of angle 1 is 50 degrees. I think I'm going to go ahead and solve for angle 2 next, because I'm noticing a little vertical angle action here. So if I could find this angle right here, I would know what angle 2 is, even though its vertex is not at the center and it's not on the circle. So it's technically an angle we haven't really learned about yet. The key to finding that angle that I put a dot in is going to be this triangle right here. We know triangles add up to be 180, so we're going to subtract out the 50 and subtract out the 30. Sorry, that looks like an 80, but it's a 30. So we're going to subtract 80 basically and end up with 100 degrees as our measure for angle 2. All right, let's finish this up here. In order to find this arc, I don't have enough arcs around the circle to be able to use 360. I don't have anything through the center to be able to use 180. So I really need to look for an angle that's attached to that arc. So if I follow this back, this angle right here is intercepting that arc. However, that angle is just in the circle at some random spot. It's not at the center, so it's not equal, and it's not on the circle, so it's not half. So that's not going to be super helpful. So I'm going to try again to travel backwards from these 2 points, but I'm going to take this path a little bit farther, and instead of coming in this direction, I'm going to travel this chord over to there. I think that's going to be a much better choice, because that 30-degree angle does have a vertex on the circle, and it intercepts the arc. So I can think about it both of these 2 ways. Again, I can say that the angle equals the arc divided by 2, or I can say 2 times the angle equals the arc. And remember, if I started to solve this first version of the equation, it would lead me to the second version of the equation anyway. 60 then equals 8x plus 4. Subtracting 4 gives us 56 equal to 8x, and then we're going to divide both sides by 8, and x looks like it's going to turn out to be 7. All right, that's it for the second day of Standard 17. Thanks for watching. We'll see you back in class.